Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we have another episode of Northwood's Scientist. You know, one of the problems that I had when I was in high school was that I always had trouble remembering the different gas laws. So I'm trying to think of a good way to try and learn them without having to just do it by rote memory, and learn them in a way that you actually understand them. Well, hi everyone. So the first thing that you have to remember about the gas laws is that they are all related. They all go back to a single formula and a single set of conditions. Let's go ahead and go over those real quick. Okay, so to get started when dealing with gases, we have to understand that we need to do them in what is called standard temperature and pressure. So, standard pressure is 1 atmosphere, or 760 torr, which a torr is 1 millimeter of mercury of pressure. And the standard temperature will be 273.15 Kelvin. Okay? Now, what is Kelvin temperature? Kelvin temperature is degrees centigrade plus 273.15. So this would essentially be 0 degrees centigrade. Okay? Now, once we have these conditions right here, and I'm going to put these in the description because it's an important thing, we can go on and start studying gases. So the very first thing that we need to do is we need to come up with a way of relating pressure, volume, temperature, and amount of gas. So we have a formula called the ideal gas law. And that is pressure times volume equals the number of moles of gas times the gas constant times the temperature. Remember, pressure is in atmospheres. Volume will be in liters. N is the number of moles. R, this is the gas constant. And T is the temperature in degrees Kelvin. Okay? So, let's see if we can figure some of these things out. What is the gas constant, do you think? How would we determine the gas constant? Let's go ahead and have a quick look. So, we're going to write up the formula again here. And we want to solve the gas constant. So how would we do that? Well, we'd have to rearrange this a little bit. So pressure and volume divided by the number of moles and temperature will equal R, correct? So let's go ahead and put some numbers in this, and we'll start off with a standard temperature and pressure and 1 mole of gas. So let's go ahead and figure this out. Okay, so we've got standard temperature and pressure, and that's going to be 1 atmosphere and 273.15 degrees Kelvin. And let's go ahead and put the numbers in. So, PV is 1 atmosphere times the volume of 1 mole of gas, which is 22.4 liters, over 1 mole, which is the number of moles, times the temperature, 273.15 Kelvin. Now, this is going to be essentially 22.4 divided by 273.15. Now, if we do the math on that real quick, that is 22.4 divided by 273.15. That's going to equal 0.082. Now, what are our what are our units for this? Okay, we're going to have atmospheres times liters over moles times degrees Kelvin. Okay, now sometimes you will see that written so that it's a little bit more complex, and I don't really like doing that simply because it adds unnecessary complexity to it. But you can sometimes see it as atmosphere times liters times mole -1 times Kelvin -1. But basically this is what it is right here. And you can easily derive that just with a blank piece of paper at test time. You know, see how long it takes? Nothing. Okay, now the first thing that we're going to do is on most of your exam questions, they're going to say if we hold this and this stable and we change these two things, what's going to happen? All right, so let's go ahead and have a look at Boyle's law, and that's the first one. In Boyle's law, the number of moles, R, the gas constant, and the temperature are all held the same. They don't change. Now, we know that PV equals nRT. Well, this right here is going to be a constant, right? Because they aren't changing. So we know that if we get right down to the bottom here, pressure 1 and volume 1 equals nRT equals pressure 2 and volume 2. Does that make sense? Because this right here is the constant, that equals that, and that equals that. So if we want to get right down to Boyle's law is P1 V1 equals E2 V2. Now, generally it gets a little bit more complex with that. They'll say, what happens if you change the pressure from 1 atmosphere to 2 atmospheres? What happens to the volume? So how would we set that up? Well, it's actually pretty easy. So we know that P1 V1 equals P2 V2, but we change the pressure and we want to know what the volume is. So we just divide that by P2 and that equals V2. Now the atmospheres and the pressure will cancel out and we'll be left with a result that's in volume. And both V1 and V2 are just volumes. Okay, so that's pretty easy. And that's Boyle's law. Now the next one is basically what happens if we hold pressure stable but we change the volume and the temperature. Okay, now once again, number of moles is stable, R is the gas constant, and we just said that we were going to hold pressure stable. So what we want to do is we want to get all of the constants on one side of this equation and all the variables on the other. So we can rewrite it like this: V over T equals NR over P, correct? This is a constant, so we know that V1 T1 equals V2 T2. Now, the first one was Boyle's law, that starts with a B. The second one is Charles' law. So let's go ahead and put this into use. Okay, so let's have a look at Charles' law and put it into a practical exercise. So that's V1 over T1 equals V2 over T2. Okay, now suppose we compress the gas so that it's half the volume that we started with. What's the resulting temperature going to be? So let's go ahead and set that up. So first thing that we want to do is we want to identify that we want to solve for T2. So it's going to end up having to be on one side of the equation, and all of the other values are going to be on the other side of the equation. So let's go ahead and write that out. Now, T2 equals V2 divided by V1 times T1. Okay? See how that all works out together? Now, we can also arrange this for volume if you wish, but it's the same basic process. Okay? Remember, just knowing the original PV equals nRT ideal gas equation allows us to derive these. So let's do it one more time. Now, the next one that we want is going to be Gay-Lussac's law, which relates pressure to temperature. So we're going to start off with PV equals nRT. Now, what we want to solve for is pressure and temperature, and everything else is going to be the same. So I think that right now you can pretty much see this is called Gay-Lussac law. So I think it's pretty obvious how we would solve for this. Okay, P over T equals nR over V. Makes sense, right? So we also know that P1 over T1 equals nR over V. So P2 T2. Let's go ahead and get rid of that. Also equals nR over V. So getting rid of the constant in the middle, we have P1 over T1 equals P2 over T2, and that's Gay-Lussac's law. And once again, let's solve for P2. That's really quite straightforward. So P1 times T2 over T1 equals P2. Okay. Another way that you can tell that you did this right is you want an answer that's in pressure. So everything other than this pressure should cancel out, and we have a T1 or a T2 and a T1. Those will cancel out the units, and we'll be left with units of pressure. And that's Gay-Lussac's law. Okay, so let's go ahead and do one more here. Now, this one here, we've got your number on this one. This is Avogadro's law. Now, since Avogadro's number has to do with the number of moles, we're going to have to assume that probably the number of moles might be involved here, right? So, in this, we've got our original equation, PV equals nRT. And what we want to solve for is going to be volume and the number of moles. Now, the rest of these will, of course, hold stable. And obviously, simply rearranging this, we're going to get V over N equals RT over P equals V2 over N2. Now, okay, so those are the basic equations that we need to use. Now, typically what you'll get in a high school problem would be a story problem, all right? So say you are in a laboratory in the Rocky Mountains and your air pressure is such and such. How many liters would 1 mole represent? So first of all, we have to figure out what is it that we're solving for, okay? We are converting a standard temperature and pressure to another set. Now, what are our variables? The first is the pressure, and the second is going to be the volume. So let's go ahead and break this down, starting with the ideal gas law. Okay, so we're going to start off right here. First, we're going to write down what is standard temperature, pressure, and volume for 1 mole of gas. Well, it's 273.15 degrees Kelvin. It's 760 millimeters of mercury, or 760 torr, that's 1 atmosphere. And it's 22.4 liters, which is the amount of gas volume that would occupy 1 mole of gas at standard temperature and pressure. So let's go ahead and set this problem up. Now we're going to start off with the ideal gas law. EV equals nRT. Now recall that we want all of our variables on one side of the equation, and we want all of our constants on the other. So what are the variables here? EV, all right. So we have a change in pressure, and we're going to have a resultant change in volume. The number of moles of gas, the gas constant, and the temperature are all the same. So they're our constant. So what do we have here? Boyle's law. So what we're going to do, instead of using atmospheres, we're going to make 1 atmosphere equal 760 millimeters of mercury, or 760 torr. So we know that PV, P1, V1, which is going to be standard temperature and pressure, equals P2, V2. Now, what do we want to solve for? We want to solve for the volume right here, V2. So let's rearrange this so that we have P1, V1 over P2. And then we'll put our numbers in. Now, P1 is going to be 760 torr, which is 1 atmosphere. And we're going to change that for P2 to 720 torr. Good. And we also know that 1 mole of gas is 22.4 liters at standard temperature and pressure. Okay? Now the first thing that you should be able to figure out with this is if you lower the pressure on a set amount of gas, you would expect the volume to increase. Okay? And it looks like this is going to be greater than, 760 over 720 is greater than 1. So let's go ahead and do this math real quick. It'll only take a second. So we've got 760 divided by 720 equals 1.055555 times 22.4. We're going to end up with 23.6 liters per mole. And that would make sense. So let's go ahead and just get rid of this real quick. And there it is, 23.6 liters. Now, our torr is going to cancel out just like the atmospheres would cancel out, and we're left with liters. And that's what our result is in, liters. Very simple to use. Now, let's look at a great way to try and get a working use of these 3 laws. Now, you should memorize which ones are variable for each law. Okay, like in Boyle's law, it's the pressure and the volume, and in Charles' law, it's the volume and the temperature. Those are things that you should probably memorize. But let's use this ideal gas law a little bit and see if we can kind of get a way to get a feel for the whole thing. So, here we go. PV equals nRT. Now, we know that R is a constant, and generally, the amount of gas is held constant. You don't add matter to the system. We're looking primarily at the changes that are caused by changes in pressure, volume, and temperature. So we can take this and bring it over here and end up with PV over T equals N and R. And likewise, we can have PV1 over T1 equals PV2 over T2. Now that's a very powerful combined gas equation right there. Because as long as you hold the amount of gas stable and the constant doesn't change, we can relate everything here because generally one of these things will also be held stable. So, for example, if the temperature is held stable, T1 equals T2, we can just kind of change that to 1 over 1, and then indeed change that to Boyle's law. See how that works? So that becomes P1 V1 equals P2 V2, right? Now, suppose we change that a little bit more. Oops, didn't want to do that. Now, suppose we hold the pressure stable. Well, what's that become now? Pressure isn't going to change. That looks kind of familiar too. That's Charles' law, right? Now we're going to go ahead and do this again. Now, again, we have P1 V1 over T1 equals P2 V2 over T2. Now, what if we hold the volume the same? What do we have then? That's Gay-Lussac's law. Pretty easy, huh? So that's an easy way to remember it. Okay, now here's a neat little trick that you can remember. So this is the combined gas law. We start off with the ideal gas law of PV equals nRT. We hold N and R constant, so it becomes PV over T equals a constant. So P1 V1 over T1, whoops, that's T1, sorry. Let's fix that. Equals P2 V2 over T2. Pretty simple, huh? Now, let's go ahead and make some changes to it. So if we hold T constant, it becomes Charles' law, or excuse me, Boyle's law. Now, if we hold P constant, it becomes Charles' law. And if we hold V constant, it becomes Gay-Lussac's law. That makes some sense? So, even if you don't remember the names of the law, and I would recommend that you do remember the names of the laws, you can easily calculate them from just knowing this one combined gas law right here and knowing the ideal gas law. The other thing, of course, that you're going to need to know is standard temperature and pressure. Because generally, when you're given a problem, you have some abnormal conditions and you have to change the properties of a gas at standard temperature and pressure to those abnormal conditions. So, this is Bob the Science Guy. I hope that this helped you a little bit with your understanding of the gas laws. And we'll see you again soon.